Hi again, it's this crazy astrophysics guy again. Yes, I am at home. It is Sunday, October 11th, about 2:30 p.m. I just wanted to let you guys in on some stuff that I was going to talk to you about in the last episode, but didn't get to. And I wanted to show you this thing about the chemical chaos that I wanted to share with you guys. This is kind of how it translates into, if you guys can see that. This is how stars actually burn. Yeah, you can see where it starts all the way at the top with H1. That's pure hydrogen with one proton. Then we go to 2 hydrogen, which is deuterium. 3 hydrogen is tritium. Then we go into helium-4, which is a heavier element, and then you just get heavier and heavier. See where the brackets are? Here, I'll actually set this down a little bit. Where the brackets are, that's where our complex conjugates are, and this is why we call it chaos, because there is this complex conjugate, which helium-4 will burn into lithium-5, but it also goes backwards. I mean, this is where oxidizing and reduction agents are actually in place at the same time. So you're getting lithium and helium and hydrogen at the same time. So you have that one major complex system. Then you can go from one, like, I'll put it here. See where it says new? This is where the new stars are. So the new stars go from hydrogen to helium. And when they start burning helium, they can actually start burning lithium as well. And they'll go all the way to boron. So when you're starting to burn beryllium and boron, and you get to the older stars, and I'll show you this as well, you go from oxygen and you're burning all the way to nitrogen. And here's another. Here's my other whiteboard of what these isotopes are. Is they actually, like the oldest stars, they actually burn silicon. So that's what Si means, and Al is aluminum, and it goes from neon. This one goes from neon, because you're burning neon. It goes into sodium for a quick spot. And then their complex conjugate is magnesium and magnesium and sodium. So it can go back and forth as well. So all of these is what the oldest stars are actually burning. Aluminum, silicon, chromium, all the way up to, it can burn all the way up to the elements of this is an infinite number. This is an infinite number of formulas. I just wanted to show you guys. What would be happening as far as astrophysically as possible. Stars do burn, all that. I just wanted to make sure that you guys knew that that was just my interpretation of what chemical chaos is. Stars do burn everything. Hydrogen all the way up to iron 56 usually is what our star is actually burning. Does it is it always burning iron? No. It can. It's a convection oven, pretty much. It's a infinite number of convection ovens. There's an infinite number of these complex conjugates that are working at the same time. You're having oxidizing, you're doing reduction, and then I know most of you are asking, well, then why does it take 100 million years for it to get for it to, in its life cycle, to get as far as it is? Well, it's burning at such a rapid pace that time really doesn't have, time isn't absolute. So when it's burning at a rapid pace, there's a lot of things going on in the same time. There's annihilation because neutrinos are coming. Everything is happening at the same time. Particles are being annihilated and eliminated. I wouldn't say eliminated. It becomes rays is what's going on there. Remember, energy is neither created nor destroyed. Even when information goes into a black hole, it does not get destroyed. It gets changed. Chemically, it gets changed. And there's a bunch of mathematics that goes along with that as well. I just wanted to make sure that I shared my chemical composition with you on the basics of astrophysics. This is as basic can get. I'm starting at Astrophysics 101 pretty much. Because, yeah, you have to know chemical compositions of what's actually happening. And I've got even pictures of, I've taken multiple pictures of the sun myself from my own telescope. I've used the right filters so you don't burn your retinas. You should never look into the sun. Never ever look into the sun. You burn your retinas that way. But yeah, I've used special filters to actually get some pictures. And I've actually got some pretty awesome pictures of firenados. Yeah, that's what I'm calling them. Firenados. They're actually like sunspots. They coincide with sunspots. These things go into hundreds of miles into space, but they're like tornadoes for us. But yeah, they actually are huge. The funnel clouds for these things would engulf the entire Earth. That's how huge these things are. These things could destroy everything, as far as we're concerned, a planet, pretty much. So these things work in multiple ways. It's just interesting on how much these things could go. And I've got multiple pictures of these. But yeah, it's very, very complex is what our star is. It doesn't rotate the same. The equator rotates a lot faster than the northern and southern hemispheres. It's plasma is what it is. It's the actual, it's like quark gluon plasma is what this is. And it's creating elements like you wouldn't believe. It's incredible what this thing can do. In its core, we'll probably find, especially when it gets older, we'll probably find massive amounts of silicone, iron 56, and I'm talking isotopically here. We're probably going to find beryllium. You never know. There's a lot that goes into this. It's massive. When you start out, like I say, when you start out with hydrogen, heavy hydrogen like deuterium or tritium, which is helium-2 and helium-3, or hydrogen-2 and hydrogen-3, that star could last for hundreds of billions of years, and our star right now is only halfway through its lifetime. And, like I say, all stars start out as hydrogen and helium. They start burning hydrogen, they start burning helium, and no matter how old it gets, whether it's burning silicon, as a stable fuel, through oxidizing and redox actions, it's always going to burn a derivative of hydrogen. Hydrogen's always going to be there. That's just a fact of the instance. So I don't understand why scientists are trying to rename older stars because they don't burn hydrogen, even though they do burn a derivative of hydrogen. It takes a long time. If you think about our star is 99.97% of the mass of the solar system, okay? So we're talking huge. This thing, we could fit infinite amount of information into the sun, and we wouldn't even be halfway into collecting everything. There's so many there. We could fit 300 times the mass of the size of the Earth, the mass of the Earth, 300 times that. I mean, that's unimaginable in our mind. This thing is huge, and fusing elements like nothing to it. And like I just showed you, the entirety of, well, it's not the entirety. I've only showed you a little bit. I mean, we go from hydrogen to helium, and like I say, the complex conjugates, they're always there. I mean, this is just out of one complex system that could spur off a whole bunch of other derivatives. It goes back and forth. They could burn from hydrogen to helium, then that helium can be broken down back into hydrogen, and it starts all over again. It's just a cycle. I am kind of, like I say, I'm also Diogenes Laertius of Goniology. So I'm also looking at this mathematically, chemically, astrophysically, quantumly. It's all there. I mean, like I say, the sun is quark gluon plasma. It's going to replicate many, many, many different things. It's a particle explosion oven is what I like to call it. Infinite. It's always going, always moving. This thing convects. It's unbelievable what you can get out of this. It actually does produce water. Yes, out of a burning sun, you can produce water. However, it condenses, it vaporizes. Yeah, it never lasts long, I'll tell you that, because the sun is way too hot. Well, I shouldn't say way too hot. You can have hotter suns, the massive red giants are a little cooler than the red. And I'll talk to you about color and all that other at a later time. I know I'm rambling on here, but the main issue I wanted to share with you guys today was the chemical chaos that does occur in the star itself. Our sun is a prime example. I want to recreate that on Earth. What I say about want, everything in fusion right now, and as of 2020, that's what I'm saying, has been toroidal, which is a torus. They're making it into a topological torus is what it is. It's not a sun. There's no core to this. There's no nothing. It's just a I can't even talk. A cylindrical circle, and where they put the plasma in, and make the plasma in. They light it, they fuse it, and all this stuff is fusing for them. Like I said, Hi-Fi used 1% of my design. which they did take the neutrino sheath that I was gonna use on my project for neutrinos. Whenever the neutrinos would hit that, it would create electricity. And with that is, if you build a big enough capacitor, you could store as amount of energy as possible. If you burn 102, I'm going to take the Hi-Fi instance just for instance here. They burned 102 seconds worth of sustainable fusion. Well, in that sustainable fusion, 102 seconds, you could power Shanghai for like 6 months off of that. So if you had an infinite, and I'm talking this thing lasts a lifetime, amount of sustainable fusion, you could have, and I know you can't really take infinity times anything, but yeah, infinity times infinity worth of hours of power. Yeah, you could. The possibilities would be endless. But yeah, as I just showed you on this chart, that yeah, we could. The possibilities are endless, especially with chemical chaos, mathematical chaos that goes along with that to describe what's going on. It is completely mind-blowing of the possibilities out there with this current energy that we could have. And just wanted to share that with you guys today. I know from the last episodes, you kind of thought things have changed. They have. I wanted to change it because I didn't think there would be a whole lot of followers if it just said Cover University. It's no longer Cover University. It's within the mind of Cover. But yeah, the message is still the same. I want to reach out to all of you and say, hey, if you need any help in anything pre-algebra wise, calculus, whatever, just let me know. And, I'm out there for you guys. I'm also out there for you scientists as well. We can share ideas, which I'm doing right now, sharing ideas, and anything else like that too. So just give me. I'll be looking at comments and questions later. So yeah, I just wanted to let you guys sink this into your mind and see what's going on, because things that I put out there, they are mind-blowing. Once you get the hang of it, and yeah, you should live in my mind for 24 hours. I'll tell you, it's no laughing matter. Even though I am kind of snickering, it's been like I said, I've got 30 years of just math diaries, let alone science diaries. Of the things that I could come up and create are 20 years ago would have been impossible, but it's getting possible right now. So, like I say, I'm writing grants for experiments that I want to do. Writing up experiments to the T. I gotta have money spot on before anybody can say, hey, we'll give you a grant for this. But yeah, I am in the process of doing that. So that's what I've been doing, on my off time, other than doing this show and working crazy hours. But yeah, it is what it is, and I didn't want to take too much of your guys' time. So always live 5 iterations above the norm. That's what I'm always going to be saying, because that's stuck with me ever since I was a kid. So always live 5 iterations above the norm. And I love you guys for following me. I love you guys. I love you all. So hope you have a great week, and I will catch you guys later. All right. Thanks a lot. Have a good one. Bye.